Good morning, everyone, and welcome to INE's webinar on carrier supporting carrier, where we would be performing some L3VPN. We will look at configuration and the basic concepts for carrier supporting carrier. For some of you who do not know me, again, my name is Rohit Pardasani, and I am a full-time instructor with INE. I have 5 CCIE, CCN route switch, security, voice, collaboration, and service provider. I've been in the industry for about 19, 20 years now, and done a lot of boot camps, recordings, and obviously consulting as well. So let's quickly get started with our webinar. Let me shut this off. So for this webinar, I would be using this topology here, where we have, I believe we have 3 ISPs. So we have ISP 2 here. We have ISP 2 here as well. And we have the core carrier, which is the core ISP, which is ISP 1. Now, obviously, there are different ways of building connectivity between customers who are geographically separate. There's inter-AS option A, B, C, but why would we actually use carrier supporting carrier? Think about it from perspective of, let's say if I have multiple ISPs, let's say I have ISP A, and there's another ISP A here. So basically the same ISP in different geographical location, but they don't really have end-to-end MPLS running. Maybe they don't want to run their own MPLS domain, or they don't have physical connectivity at some point of time, maybe somewhere in the center. So what happens with carrier supporting carrier is that I'm actually giving connectivity to customers of a smaller ISP through a bigger ISP. So ISP 2 here would be called as the customer carrier because he has a customer. And ISP 1, which is here, would be called as the core carrier, which is basically giving connectivity to ISP 2, which is geographically separate. So ISP 1 would be called as the core carrier, and ISP 2 on both sides would be called as the customer carrier because they have customers. Now, the whole advantage of this is that it becomes highly scalable, because now I can have, I don't really need to have ISP 2 end-to-end running MPLS, running BGP. I could just have ISP 2 connecting to the core carrier, and he would probably give us connectivity with his MPLS domain to the remote side or to the remote ISP of my domain on the other side. So that's the whole concept of carrier supporting carrier. That's why it's called as that, CSC, because we are actually giving connectivity to customer carrier and their customers running, basically running L3VPN through the core carrier. Now, implementing carrier supporting carrier is pretty straightforward. It's not really that complex. It kind of looks a lot to do from configuration perspective, but it's really not. Because if you, let's say, if you know inter-AS option B and option C, if you really know that, then carrier supporting carrier is pretty much the same thing. So what's going to happen is that the customer carrier, the true PE in the customer carrier. Who is a true PE? The R11 here would be the true PE because he actually connects to the customers. So R11 in ISP 2 would be called as the true PE for ISP 2. And he connects to the customers here. Similarly, on this side, on the right side, ISP 2 has the true PE as XR4, which is connecting to the customers. So he would be called as the true PE for the customer carrier. Now, in carrier supporting carrier, what's going to happen is these two routers, even though they are not really connected to each other in one maybe MPLS domain, they are geographically separate. There's not one MPLS domain end to end. There's no IGP running end-to-end between R11 and XR4. So what's going to happen is that we would establish a VPN v4 neighborship between them so that they can exchange labels for their customer routes, and they can exchange routes with each other. Now, obviously, for achieving the VPN v4 neighborship, we require connectivity. We require some kind of connectivity because they don't have routes to each other. There's only IGP running here. There's IGP running internally within ISP2, but there's no IGP all the way from R9 within core ISP1. Because think about it, the core ISP is not going to run an IGP with anyone. They're only going to run IGP within their domain. They would only run MPLS or segment routing or something only within their domain. They would not run IGP with anyone, with whether it's a customer or it's a customer carrier. They would not run that, which means my transport label is basically broken. And obviously, I don't have reachability between R11 and XR4. So the whole job of the core carrier is to first give connectivity for R11 and XR4, the true PEs of the core of the customer carrier connectivity, so that they can establish a VPN v4 neighborship. At the same time, they would also treat the customer carrier as a customer. So from the core carrier's perspective, I would treat the customer carrier as a customer. So basically there would be VRFs coming in play, and there would be L3VPN also. You'll actually see a lot of label stacks, which I would discuss once we do some configuration and I show you how it actually works. So what we would do is establish a VPN v4 neighborship between the true PEs of the customer carrier. Now, obviously, to establish this, there has to be connectivity. That is done by the core ISP. So what's going to happen is R9, which is not a true PE. He's not a PE. He's not really connecting to any customer. He's just a normal router, which maybe connects to the core carrier. So R9 has reachability to R11's loopback because there's some kind of IGP running within ISP2. I believe in my configuration, I have used OSPF here. And even here, I have used OSPF internally within ISP2. So R9 and here would be XR1. They both have reachability to their respective true PEs through IGP. And there's obviously MPLS also running within the ISP domain. So since R9 has reachability, he would advertise the route to the core ISP through BGP. So he would establish a BGP neighborship with the core ISP. And this BGP neighborship would not just be a normal IPv4 BGP neighborship. This would be a labeled unicast BGP neighborship. So basically you would do a send label. Now, why are we doing a send label? Think about it. Is there MPLS between 9 and R2? The core ISP and the customer carrier? There's no MPLS there. There's no IGP there. So if I just advertise a route without a label, what's going to happen? My transport label is going to be broken, which means that I would have routes. Both the customers would have the routes in their routing table. But when they actually try to ping, that ping is not going to work because the traffic would come to R9 and probably get dropped because it's going to be an IP packet or a VPN labeled packet going to R2, and R2 does not know anything about the VPN label which XR4 has assigned to R11. Because R11, which is the true PE of ISP2 on the left side, and XR4, which is the true PE of ISP2 on the right side, they both are establishing a VPN v4 neighborship with each other, which means they would exchange VPN labels with each other only. So the core ISP does not really know about the VPN label because there's no VPN v4 neighborship with the customer carrier. There's no VPN v4 neighborship. So obviously, if R9 sends a VPN labeled packet to the core carrier, it's going to be a problem. It's going to be broken. R2 would just drop the packet. So because I'm not running MPLS, I have to maintain the transport label end to end. And that's going to be done through BGP. So there would be a labeled unicast between R9 and R2. So this would be, again, IPv4 BGP labeled unicast BGP neighborship between 9 and 2. Similarly, between 5 and XR1, I would have an IPv4 labeled unicast BGP neighborship between the core carrier and the customer carrier router. So once I have the BGP neighborship, what's going to happen? R9 has the route of R11 through IGP. He is going to advertise that route to the core carrier R2. Similarly, XR1 is going to advertise the route, the loopback of XR4 to R5 with a BGP label. Now, what is R2 and R5, which is the true PE of the core carrier? What are they going to do with that? They would just normally treat the customer carrier as a customer. So basically, I would have a VRF created here. So this interface goes in a VRF. This interface would go in a VRF. And your core ISP would treat the customer carrier as a customer. Now, obviously, 2, which is the true PE of the core carrier, and R5, which is the true PE of the core carrier, they would establish a VPN v4 BGP neighborship with each other. That's how R9 would learn about XR4, because XR4 gives the route to XR1 through IGP. XR1 would advertise that route in BGP with the labeled unicast, with the label basically to R5. R5 would encapsulate that with a VPN label and send that to R2. R2 would remove the VPN label and send that to R9. And then R9 would redistribute that one specific route into IGP, which is OSPF, and XR1 would redistribute that in IGP in OSPF. That's how R11 and XR4 would know about each other, with the transport label being end-to-end, because I have MPLS from 11 to 9, I have BGP labeled unicast from 9 to 2, I have MPLS again running within core ISP, then from 5 to XR1, I have BGP labeled unicast, and then within ISP2, I have MPLS running again, so my transport label is end-to-end. That's the whole concept of core carrier. So if you look at from perspective of what do I need to do to build your carrier supporting carrier, what do I need? Think about this diagram. What do I need? The true PEs of the customer carrier would establish VP and V4 neighborship with each other. For them to establish the neighborship, I need to give them reachability. So 9 and XR1, which is the edge router connecting to the core ISP, they would form an IPv4 labeled unicast BGP neighborship and advertise the route to the core ISP. The core ISP would treat the customer carrier as a customer, create VRFs, build a VPN v4 with the true PE on the other side, advertise that route there, and then the route would go back to R9. And then R9 and XR1 would redistribute that in IGP. And that's how 11 and XR4 can establish the VPN v4. So this is the whole configuration perspective, what you need to build your carrier supporting carrier. That's all you really need. So let me in fact show you. So I'll actually build this. I'll build this completely from the scratch. I believe what's pre-configured right now in my configuration, I have, I believe I don't have any BGP configuration done. There's no BGP configured at all. There's OSPF running here plus LDP. There's OSPF running here plus LDP. There is, I believe there's OSPF here also and LDP. So that's what is pre-configured at this point of time. Now for building L3VPN, think about 6 steps. It's a 6-step process. Step number 1 is creating a routing table for the customer. So I would create a routing table for the customer. On where? On the true PE. So who are the true PEs here? I have R11, which is a true PE for ISP2 on the left side. I have XR4, which is a true PE for the ISP2 on the right side. I have R2, which is a true PE for core carrier. I have R5, which is a true PE for the core carrier again. So these are my 4 true PEs. So step number 1 is basically creating the routing table for the customer. That's your step number 1. Step number 2 would be to move the customer facing interface in that routing table. So basically your interface goes in the VRF. So move it from the global table to the routing table of that VRF. Step number 3 would be learning the route from that customer, which would be the PECE routing protocol, the PECE routing protocol. Step number 4 would be establishing VPN v4 neighborship between the true PEs. Step number 5 would be redistribution, mutual redistribution. And step number 6 is your import export. What do you need to import? What do you need to export? Basically your route targets. 6-step process. So always remember the 6 steps. Don't think about anything else. Think about the design. So let's say if you were given the task of configuring carrier supporting carrier, I would tell you to remember this diagram, remember the things that I told you, that what you need to do to build this, and then think about 6 steps. What do I need? So that's what I'm going to be doing. So I will start off with the true PEs, which is R11 and XR4, and do step number 1, which is creating the routing table for the customer. So let's start with R11. So I'm going to show you my configuration first. So if I look at R11, let me first expand this and make the screen a bit bigger, so maybe you can see better. Let's make this 18. All right. So if I look at R11 and do a show IP route OSPF, I have OSPF running internally on all the internal links within the customer carrier, which is R11, R10, and R9. I have their loopbacks in my routing table. If I look at my MPLS forwarding table, I have MPLS already pre-configured. Again, MPLS is only running within the ISP, not on their links towards customer, not on their links towards the core carrier. I have only MPLS running within the internal network. So first thing that I would do is step number 1 is on the true PE R11. He has 2 customers. He has customer yellow and customer green. So he has 2 customers. So I would first create the VRF, create the routing table. So if I look at my routing table right now, show IP route, let's say VRF star, I only have the global table right now. All my interfaces are in the global table right now. I only have one routing table, which is the global table. So step number 1 is creating the routing table for the customer, because I really want to separate the routes of the customer. I don't want all my customers be in the global table, because then if I'm running OSPF with customer 1 and I'm running OSPF with customer 2, then OSPF routes would be exchanged between customer 1 and customer 2. You don't want that. You want to separate the routes. So I would create 2 routing tables, one for customer yellow, one for customer green. Let's do that. Now you could do an IP VRF, or you could do a VRF definition. Again, that depends on whether you want address family IPv4, or you want address family IPv6, or you want both. IP VRF only supports address family IPv4, and VRF definition supports IPv4 and IPv6. I'll just do VRF definition. Even though we would not be using IPv6, we'll only be using IPv4. I don't need to activate IPv6 if I'm not using it, but I'll still use VRF definition. Let's create 2 of them. So yellow, and I would give a route distinguisher. Again, let's use the route distinguisher as maybe my local router and remote customer's router number, which would be, let's say 11 colon, so yellow is 13. So 13. Again, you could use just any arbitrary number, it doesn't really matter, but I'm just going to use it for the sake of simplicity. So I'm using the local router number and the remote router number as the route distinguisher. That's my step number 1. And obviously activate your address family, IPv4, unicast. I'm not activating address family IPv6 because I don't need that right now. Let's create one more VRF, which is going to be green. Route distinguisher would be 11:12 and address family IPv4 unicast. So I have done step number 1. Let me quickly show you that. That's my step number 1 that I did. I created the routing table. Obviously, you can verify that with show IP route VRF star. You would see 3 routing tables now. One is the global routing table. One is the routing table for yellow. One is the routing table for green. This is my global routing table. And this is my routing table for green. There's nothing inside that right now. And this is the routing table for yellow. There's nothing inside that right now. That's my step number 1. Step number 2 was moving the customer-facing interface to that routing table. Right now, my customer-facing interface is in the global table. So I need to move that from the global table to the routing table of yellow or green. That's step number 2. So let's just do step 1 and step 2. And on all the routers, on all the true PEs, and then we can do step 3, 4 on all the routers again, the true PEs, and then step 5 and 6. So R11 is done. Let me go to the interface. I believe the interface facing yellow is 11.13. So interface gig 1.11.13. This would be VRF forwarding. So VRF forwarding, yellow, and IP address would be, I believe it is 10 dot something. Let's check. So it is 10.11.13.11. So 10.11.13.11, 255.255.255.0. Let's go to the second interface, which is green, which is 11.12. VRF forwarding green. And IP address would be 11.12.11. So I've done that. Step number 2 is done. I've moved the customer-facing interface from the global routing table to the respective routing table. How do I verify that? Just do a ping, back-to-back ping to the customer. So let's do a ping to VRF yellow to 10.11.13.13. I should be able to ping the customer edge. So I can ping, and let's ping green also to 10.11.12.12. I should be able to ping customer green also, which I can. So step 1, creating the routing table, and step 2, moving the customer-facing interface in that routing table is done. Let's do exactly the same thing on the other side true PE, which is going to be XR4. Let's go to XR4 and do exactly the same thing. Obviously, the concept on XR routers is the same, like XZ. The commands may be different, but the concept of what you need to create is the same. So let's check if there's any VRF pre-configured. There's nothing, so let's create that. So I would go and say VRF yellow. And what did we give inside the VRF on R11? We give the route distinguisher and we activated the address family. That's all we did. In XR routers, the route distinguisher is not given under the VRF. It's given under BGP. So that's the only difference. So all we do is activate address family IPv4 unicast. That's it. I don't define the route distinguisher. That's going to be under BGP. So if you want to be, let's say you want to follow a sequence of steps so that you never forget, what you could do at this point of time is exit out, create the VRF green also, and say address family IPv4 unicast, and then maybe go to BGP, router BGP 12345, and just say VRF yellow, and define route distinguisher 34 colon, I believe XR4 is 34, and yellow would be R18, so 18, and then exit out and say VRF green, and say route distinguisher would be 34 colon 17. So this kind of makes your sequence of steps similar. So the only difference was that I don't really give the route distinguisher under the VRF, I give it under BGP in the VRF yellow and green. And let's do a commit. So step number 1 on XR4, which is the true PE for ISP2 on the right side, is done. Now all I do is move the customer facing interface in that respective VRF. So that's going to be done by show run interface gig0000 dot, I believe it is 1834. So this is the customer facing interface. Let's go and put that interface in the VRF 1834. That's going to be VRF yellow. And IPv4 address would be 10.18.34.34.255.255.255.250. Same thing I would do for 1734. This would go to VRF green. And IP address would be 10.17.34.34. Let's commit. Step number 2 is done. So now I have customer-facing interface in that respective VRF. Again, I could verify this with a ping. So I could probably go and say ping VRF yellow and do a ping to 10.18.34.18. I should be able to ping the remote customer back to back. That's my step number 2. Let's look at step number 3. I'll configure the core ISP maybe later. I'll finish off the true PEs of the customer carrier. So what's step number 3? Okay, now I have back-to-back connectivity with the customer. What's next? Learning the route from the customer, which means a PE-CE routing protocol. So you got to think of, what am I using to learn routes from the customer? Am I using BGP or am I using IGP? So from perspective of real world, obviously it would either be a static route or it would be BGP. You would never have an ISP running OSPF with the customer. In a lab environment, let's say maybe a CCIE or maybe a CCNP, you may have even IGP as the PE-CE routing protocol. So in our case, what we'll do is for yellow, we would use BGP. So PE-CE would be BGP. For green, we'll use maybe OSPF. OSPF as the PE-CE routing protocol. So it just gives us a flavor of both scenarios. Let's do that. So let's start with the customer. So customer on the left side is R13, which is here. I believe there's no protocol running right now. There's nothing running right now. All I would do is normal BGP. It's just a normal customer edge running normal global BGP. There's no VRF on the customer side. So he would just run BGP, router BGP, let's say 13. And neighbor would be the core, your customer carrier PE, which is R11. So 10.11.13.11. Remote AS would be 12345. And let's advertise all my networks. So maybe I can do a redistribute connected. So it just advertises all my routes. That's all I need on the customer. And on R12, I'm running OSPF. So let's do that also. So router OSPF 1, network would be 10. I believe it's 11.12.12. area 0, and my loopback 12, 12, 12, 12, area 0. So my customers are basically advertising the route to the customer carrier through BGP, which is yellow, and through OSPF, which is green. I configure my customer carrier with that respective routing protocol under that VRF so that I can learn the customer routes. So for yellow, we were running BGP. So router BGP 12345. I would say address family IPv4 VRF yellow. Why am I doing it under the VRF? Because the customer facing interface is in the VRF yellow. So neighbor 10.11.13.13, remote AS 13. At this point of time, I should learn the customer route through BGP on R11. Let's check that. Show BGP VPN v4 unicast all. So I have learned the customer route, which is the loopback of the customer. I have learned that route through BGP. So my true PE of the customer carrier has learned the route. Same thing I would do for OSPF. So run router OSPF. Now again, be careful with your OSPF process because I'm already running OSPF internally within ISP. So don't use the same process ID. It needs to be a different process ID and not global OSPF. It needs to be a VRF enabled OSPF. So let's just use router OSPF 11, VRF green, and say network 10.11.12.11, 0000, area 0. So I should learn the customer routes, show IP route, VRF green OSPF. I should learn the customer routes, which I am. So step 3 on the true PE is done. I am learning the customer routes. Let's do on the right side also. Let XR4 learn both the customer routes. So once they learn the routes, what are they going to do with that? They need to exchange those routes, their customer routes, with each other, which means R11 and XR4 need to exchange those routes. That's going to be done with VPN v4 neighborship. So let's go to customer R17, which is green, running OSPF. So router OSPF 1, network 10.17.34.17, 0000, area 0, and network 17, 17, 17, 17, area 0. Let's run R18 also. We'll run BGP here for yellow. So router BGP 18. Neighbor would be 10.18.34.34, remote AS 12345, and then redistribute connected. So customers are done. All I need to configure now is XR4 so that he receives the routes through the PECE routing protocol. So here, if you look at my BGP configuration right now, the only thing I had done in my step 1 was created the VRF and did route distinguisher. That's all I did. So now what I need is to establish the BGP neighborship. So for yellow would be BGP. So router BGP 12345. I would go under VRF yellow and say address family IPv4 unicast. And I would need neighbor 10. I believe yellow is 18. So neighbor 10, 18, 34, 18. Remote AS would be 18. And address family IPv4 unicast. And because it's an eBGP connection, think about what do I need? Think about it for 1 minute. What do I need if it's an XR router and it's an eBGP connection? By default, XR routers have an inbuilt filtering, which basically filters any routes learned from an eBGP neighbor or any routes being sent to the eBGP neighbor, which means I need a route policy. on my XR4 to learn the route. Otherwise, even if R18 sends the route, XR4 would discard those routes. That's an inbuilt filtering mechanism on XR routers. I only need route policies for eBGP neighborship, not for iBGP. So I'm going to go and say under this saying route policy, let's name this as pass in and pass out. I obviously need to create that route policy. Let's exit out completely and say route policy pass. And a simple policy just says end policy. So there's really nothing. I mean, I'm just putting pass and end policy. So there's no condition as such. I'm just saying like a permit all. There's no really any condition in the route policy. The only thing I'm putting in is saying pass. So any routes being received or any routes being sent, allow those routes. Now I need to commit. I think my commit would fail. The reason this would fail is because I haven't really activated the address family globally. That's one thing on the, again, that really depends on the version of the XR router you're running. So if I look at show configuration failed, it should tell me that I have not enabled address family globally. The address family has not been initialized globally. So router BGP 12345, address family IPv4 unicast, exit out, address family VPN v4 unicast, and let's do a commit. I'll show you my configuration, what I did on my XR4. So show run router BGP. Look at my config now. So this is what my config looks like. So I have router BGP, then I have globally activated address family IPv4 and VPN v4. I don't need the VPN v4 right now, but I would need it eventually. So I just put it right now. I have the VRF green, I have VRF yellow. For yellow, we are running BGP. So I have activated address family under the VRF also and under the neighbor also. So if I don't do this, I can't give this command. And if I give this and I do not give this globally, it won't let me commit again. So I need this globally, I need this under the VRF, and I need this under the neighbor. Again, this really depends on the version of the platform you're using. In my version, I need it on all three places. Otherwise, it does not really let me commit. Again, that depends. But you would at least need this, and you would need this. This depends on the version. So if I look at now, show BGP IPv4 unicast, show BGP I should have a route. I do have a route in my routing table of yellow, which is learned through BGP. Now I need to run OSPF with green, and that would complete my step number 3 on the true PE of ISP2. So router OSPF, let's say 34, VRF green, and address family IPv4 unicast, area 0, interface would be gig 0000.1734. Once I do a commit, I should learn the customer routes through OSPF. So show route VRF green OSPF. I should have the routes in my routing table. So I do. Step number 3 is done. So now both the true PEs, R11 and our XR4, they are learning the routes from the customer. One customer is running BGP, one customer is running OSPF. So I'm learning the routes. What do I do with these routes now? I need to give it to someone. Who is that someone? See, XR4 is a true PE. he has no relationship with the core ISP. For him, it's the my ISP itself, which is on the remote side. So the true PE XR4 would establish a VPN-v4 neighborship directly with R11. So R11 and XR4 would form the VPN-v4 neighborship so that they can exchange those routes. So I would do my step number 4 now, which is VPN-v4 neighborship. Obviously, that neighborship would not come up at this point of time because the core ISP has not been configured yet to learn the routes to allow VPN-v4 routes to be formed. So, but I would still configure it. So let's go to R11 and go to router BGP 12345 and let's do a no BGP default IPv4. Unicast. So I don't need an IPv4 BGP neighborship with XR4. I only need a VPN-v4. If I had global routes being exchanged as well as VRF routes being exchanged, then I would need both the neighborship, IPv4 and VPN-v4. In our case, all my customers are inside a VRF, which means I only need to exchange VRF routes. So I would only establish a VPN-v4 neighborship. But yes, maybe let's say if R11 connected to internet through the core ISP, maybe there was internet through the core ISP, and there were global routes being sent by the core ISP to the carrier ISP. In that case, I would need IPv4 BGP neighborship also. But in our case right now, we don't really need IPv4. We only need VPN-v4. So let's do neighbor 34, 34, 34, 34, which is XR4. Remote AS would be 12345. Update source would be loopback 0. I don't need eBGP multi-hop because they are iBGP neighbors. So R11 and XR4, they both are in the same AS. They're the same ISP, ISP2. So they're in the same BGP AS number. So I don't need eBGP multi-hop. I just need update source loopback 0. And then address family VPN-v4 unicast, neighbor 34, 34, 34, 34, activate. That's all I need to establish my step number 4. Let me quickly show you. That's what I configured for my step number 4 on R11. Same thing I would do on XR4. So go to my router BGP 12345 and give the command neighbor 11, 11, 11, 11, 11. Remote AS would be 12345. Update source would be loopback 0. Address family would be IPv4. In fact, this would be VPN-v4 unicast. I don't need route policy because this is iBGP neighborship. That's all I need. Commit. So if I look at my BGP configuration on XR4, this was green and yellow. This is my configuration that I did for my VPN-v4 neighborship. Now, obviously, this neighborship is not going to come up because I don't have reachability at this point of time. If I look at my routing table, my global routing table, show route OSPF. If I look at this route, I don't have 11, 11, 11, 11 in my routing table because IGP is not end-to-end, BGP or MPLS is not end-to-end. So I need some way to send the routes loopback of R11 and loopback of 34, which is XR4. I need those routes to be sent to each other in some way. That's going to be done by R9, which is the core carrier's edge connecting to the core ISP, the customer carrier's edge connecting to the core ISP, and by XR1. So how would I do that? So I would first go to R9. So in fact, let's do one thing. Let's not look at R9 first. Let's complete all the steps. So we are done with R11 and XR4. So we made step number 4. What was step number 5? Step number 5 was mutual redistribution, basically sending the routes. Obviously, R11 will not be able to send the routes right now to XR4 because there's no VPN v4 neighborship, but I can still configure it. Because once the neighborship comes up, then yes, the routes would be exchanged. So I can do my step number 5 right now, which is mutual redistribution. For yellow, I don't have to do step number 5 because BGP. There's no redistribution required. So there's no step number 5 for BGP. If your PECE is BGP, there's no step number 5. But if your PECE is not BGP, in our case for green, it's OSPF. In that case, I have to redistribute OSPF to BGP and BGP to OSPF. So I would do that for green, not for yellow. So I go back to 11 and go under my BGP for green, router BGP 12345. And this would be address family IPv4 VRF green, and say redistribute OSPF, I believe it's 11, VRF green. Now you can just leave it here. In this way, he would redistribute internal routes and he would redistribute external routes, but he would not redistribute not so stubby routes. So again, that depends on what the customer is advertising to you. If he was advertising not so stubby type 7 routes, then you would not redistribute that. So I kind of have the habit of doing match internal, external, and NSSA external. So basically match all routes, whether it's an internal route, intra area, or inter area, or external route, type 5 or type 7, doesn't matter. Redistribute from OSPF to BGP. And I would also go to my OSPF and redistribute BGP to OSPF, which is here. Redistribute BGP 12345 subnets. So whatever BGP routes are there in VRF green, redistribute them to OSPF. So step 5 is done. I didn't have to do any redistribution for yellow because I was running BGP to BGP for PECE routing protocol. Step 5 is done. What's step 6? Import, export. What routes do you want to export through BGP, and what routes do you want to import? So basically enabling your extended community. So that's your step number 6. Let's do that also here. That's going to be under the VRF. So VRF definition. Let's go to yellow. And under address family IPv4 unicast, let's say route, target, both. Let's keep this as, so yellow is what? 13 and 18. So let's keep it as 13:18. And let's go to VRF definition green. This should be under address family IPv4 unicast. I would say route target both 12:17. Step 6 is done. I've done the import export. Ensure whatever export you do on R11, XR4 needs to import that. And whatever XR4 exports, R11 needs to import that. I'm just keeping it same on both sides just for simplicity. But if it's different, then you need to export. One guy would export, the remote guy would import that route target. Let's go to XR4 and do our step 5 and 6. So again, on XR4 for yellow, I don't have to do anything, step 5, because BGP, but for green, I need to redistribute. So show run router OSPF. Go back here under my green of OSPF and say redistribute BGP 12345. And then go to BGP under your VRF green, where you would say address family IPv4 unicast And you would give the redistribute command, redistribute OSPF 34, and enter, commit. So step 5 is done on XR4. Step 6 is just import export. So 6 steps. Let's do that also. So our basically 2 PEs are completely done. I don't need to touch them. So that's going to be VRF green. And that's going to be address family IPv4 unicast, import route target. I believe we used for green 1217, and export route target 12:17. Let's do the same thing for yellow. Import would be 13:18, and export would be 13:18. Commit. So all 6 steps done. Let's quickly recap the 6 steps. Step 1 on my R11 was creating the routing table. So creating the VRF yellow and green. Step 2 was moving the customer facing interface in that VRF. Step 3 was learning the customer routes through a PECE routing protocol. Step 4 was establishing a VPN v4 neighborship between the true PEs, which is R11 and XR4. Step 5 was mutual redistribution between the PECE routing protocol. And step 6 was import export. So 6 steps is what I've done on my true PE on the customer carrier. Now, all I need is to ensure that R11 and XR4 have reachability to each other. That's going to be done by R9, the core carrier, and XR1. So now let's start with R9. So if I go to R9 and if I see right now what's pre-configured, I have OSPF running internally and I have MPLS running internally, but there's nothing running on the link between R9 and the core carrier. There's nothing running there. So if I do a show MPLS interfaces, the only interface running MPLS is the link towards ISP2, not towards the core carrier. And if I look at my routing protocol, show run section router, I'm only running OSPF right now. There's no BGP right now. So the first thing that I would do is run BGP. So this could be any BGP. It doesn't need to be 1, 2, 3, 4, 5. It could be any BGP AS. But again, because it's the customer carrier ISP, I would probably have the same BGP AS. There's no BGP running between 11 and 9. 11 and 9 have no BGP neighborship. They're only running IGP. So R9 is only running BGP with the core carrier. So let's use 1, 2, 3, 4, 5. Now, a common mistake here is that we establish the neighborship, but we do not do a send label. Now, why do I need to do a send label? Think about it. There's no MPLS between core carrier and the customer carrier R9. If there's no MPLS running, there's no IGP, there's no MPLS running, my transport label is going to be broken, which means the core carrier would be exposed to the VPN label which the true PE of the customer carrier have exchanged. The core carrier would be exposed to that VPN label, and he has no idea about that VPN label because R2 is not forming any VPN neighborship with XR4 or R11. He has no relationship with them. So obviously, he cannot be exposed to the VPN label. So that's why I need to ensure that my VPN label on top of that is my transport label. There's no MPLS there. So I need to ensure that R9 generates a label when he is advertising a route. And because there's no LDP, I need to generate the label through BGP. So R9 is going to do a neighbor to 100.2.9.2, which is the core ISP. Let's do a remote AS. I believe the AS is 100. So 100. and advertise the loopback of R11. How does he know the loopback of R9? Through IGP, because I'm running OSPF. So R9 has the route in his routing table. So he can advertise that route to that neighbor. So network 11.11.11.11, mask 255.255.255.255. Now, one thing I need to do, I don't want to advertise this route just as it is. I want to advertise this route with a label. So I need to ensure that I give send label. If I don't do this, BGP will not generate the transport label required for that route. He's going to advertise the route without a label for that route, which means R2 is going to be exposed to the VPN label by the true PEs of the customer carrier, which you don't want. Otherwise, route is going to be dropped. So I am telling R9, advertise this route and send a label for this route. That's all I need on R9. Let's save this. Let's go to the other side, which is XR1. And even he will advertise the route to R5. So let's go to XR1 and do exactly the same thing. How does he know about XR4? He knows about XR4 through OSPF because he's running IGP internally. So if I do a show route OSPF, I know about XR4 through IGP 34, 34, 34, 34. So all I need to do is run BGP with the core ISP. I believe I don't have BGP right now configured. Yeah. So router BGP 1, 2, 3, 4, 5. What's the thing that I need here? So first, address family IPv4 unicast, activate IPv4 unicast globally. That's the first thing. Then I would say network, advertise 34, 34, 34, 34 / 32. And you remember we did one more thing. We did send label on R9. We need to do exactly the same thing here. However, the command on XR routers is different. Concept is the same. The command is different. The first command you need to do is allocate label all. By default, XR routers will only allocate a label for the routes that you have in your routing table and which are /32. So the first thing that you need to do is activate. Even if I do a send label, it's not really going to send the label for that route. You need to, like how we activate the address family globally, the same thing, you need to activate the address family or allocate label globally first. So you would first say allocate label all. That's the first thing you do. The next thing I would do is form the BGP neighborship with the core ISP, which is going to be, I believe it's R5. So that's going to be done with the neighbor command. So neighbor 100.5. I believe it's 31.5. Remote AS 100 and address family. So here is where I would do address family IPv4. Do not do unicast because we need to do send label. The command is different. It is IPv4 labeled unicast. So globally, I'm activating IPv4 unicast. There's no global labeled unicast. There's only address family IPv4 unicast or VPN v4 unicast. But under the address family, under the neighbor, I would say this is not a normal IPv4 BGP neighborship. This is a labeled unicast BGP neighborship. Now, obviously, this is a eBGP connection, so I do need a route policy. Let's just make a route policy. Route policy pass in, pass out. And let's create the route policy. I believe I don't have that. Route policy pass. Condition is just pass end policy. Commit. Let me show you my BGP config, what I did on XR1. Show run router BGP. This is what I configured on XR1. So now XR1 is doing exactly the same thing what R9 is doing. R9 is sending the label and advertising the route. XR4 or XR1 is sending the route and advertising a label for that route. The commands are different on XR routers. So you need to do two things. One is allocate label. Without this, even though you have this command, he would not allocate the label because it's kind of like disabled, even if you have label unicast. So you need to activate allocate label all. And then I have IPv4 label unicast. So this is equivalent to send label command. Remember that send label is negotiated in BGP. So if you have send label on one side and you don't have send label on the remote side, your neighborship would not form. So let's say if I just go here and give this command and I go to R5 and I don't configure send label, I just configure neighbor statement, my neighborship would not come up. If I don't have send label on both sides, my neighborship will come up as IPv4 without labels. But if I have send label on one side and send label is not there on the other side, they would not form BGP neighborship because the send label attribute or capabilities is basically exchanged when they're forming neighbors. So if one router has the capability for labeled unicast and other one does not, they would not form neighborship. In fact, you can see that if you do a debug BGP neighborship or maybe debug BGP events, we'll be able to see that capability mismatch that one guy has labeled unicast enabled and the other guy does not. So they would not form neighbors. So be careful with that. Ensure you have labeled unicast on both sides. So R9 and XR1 is done. What do I need now? I need now to configure core ISP. In fact, there's one more thing that I need to do on R9 and XR1, which is redistribution. Because when they learn the route, they have to redistribute that in IGP. Only then R11 will learn about XR4. I'll do that later. Let's now configure core ISP. Now, from the core ISP, it's really straightforward. It's like, think about intra-AS L3VPN. If you've ever configured intra-AS, which means one ISP only. So I am the ISP, you're the customer. Same, 6 steps. So core ISP would basically treat R9 as a customer, and he would treat XR1 as a customer. And because he's a customer, I need to separate the customer route. Because think about it, the core ISP will not have just one carrier ISP as a customer. He may have many carrier ISPs as customers. So he cannot keep the carrier ISP in the global table. He has to separate each carrier ISP separately. So I would need to create a VRF. So again, 6 steps on my core ISP, because they would treat the customer carrier as a customer. So let's go to R2 now. And what's the step number 1? Creating a routing table for the customer carrier. So let's do that. VRF definition, let's name this ISP2. This is my customer, ISP2. Route distinguisher, let's keep it as 2:, I believe it's 9, to my router and the remote router. And that's my step number 1, address family IPv4 unicast. So step 1 is done. What was step 2? Moving the customer facing interface in that routing table. That is going to be gig 1.29, this interface here. So gig 1.29, VRF forwarding, ISP2, and IP address 100.2.9.2. Step 2 is done. Let's do exactly the same thing on R5, step 1 and 2. So VRF definition ISP2, route distinguisher would be 5:31, and address family IPv4 unicast, and that interface gig 1.531, VRF forwarding ISP2, and IP address 100.5.31.5. So step 2 is done. Step 3, routing protocol with customer, learn the customer routes. What was my customer R9 and XR1 running? Labeled unicast BGP. So I should be running BGP with the customer, labeled unicast BGP. So on R5, router BGP 100. I would do address family IPv4 VRF ISP2 neighbor 100.5.31.31 remote AS 12345. Now see this. I have not given the send label. Do I form neighbors with XR1? Let's wait and see. If I do a show BGP VPN v4 unicast, can you see this? I get a message, unsupported or disjoint capability, because remote guy is using labeled unicast and I'm not. My neighborship would not form. It would just keep getting reset and neighborship would not form. So it's good that it actually gives me a notification without me actually doing any debugs. I've seen some iOSs don't do that. So I'm going to go back to my BGP and go back to my address family and say neighbor 100.5.31.31 to send label. Once I do this, my BGP neighborship should come up and I should learn the customer route with a label. So my neighborship just came up. Show BGP VPN v4 unicast all. I have the customer route, which is 34, which is the true PE on the other side. So XR1, who is learning from OSPF, is sending the route via BGP with the label. Let's check the label. Show BGP VPN v4 unicast all labels. I should see a label. Look at the label here. This is my label. So what I've done, what I've pre-configured, I've configured MPLS with a unique label range for each router so that you're able to identify them when we actually do a debug or do a trace route. So basically, all the routers, like for example, R2 has a label range of 2000 to 2999. R3 has a label from 3000 to 3999. R5 has a label from 5000 to 5999. XR1 has a label from 31,000 to 31,999. XR4 has a label from 34,000 to 34,999. So basically, I've given every router a unique label range. So now if I look here, I know that this label was advertised by XR1 because 31,000 is 31,005. So it's a label coming from XR1 through BGP. So I do see the label here. So step number 3 is done on R5. I'll do the same thing, step number 3 on R2. Run BGP with the customer. So address family IPv4 unicast. This should be, in fact, not unicast. This should be VRF ISP2. And neighbor 100.2.9.9, remote AS 12345, and send label. Let's check. My BGP neighbor should come up. And if I do a show BGP VPN v4 unicast all, I should learn customer route, which is 11. So R9 is advertising 11.11.11.11 to R2. And I should see a label for that. So if I do labels, I should see a label 9002. So you see this label has come from R9. I know that because of the unique range I gave in the initial config. So now the core ISP has learned 11 and 34. Now what do they need to do? They need to exchange with each other. So R2 has learned, R2, I believe, where is it? R2 has learned about 11 and R5 has learned about 34 from XR1 and R9 respectively. But 2 and 9 or 2 and 5, they haven't exchanged those routes with each other because they are not BGP neighbors yet. So now I go to step number 4. What was step number 4? The true PEs will form VP and V4 neighborship with each other, which means 2 and 5 would form VP and V4 neighborship with each other to exchange those routes. Let's do that. My laptop is going to conk off. 1 minute. I need to charge my laptop. Okay. Otherwise, you would lose me. Okay. So going back to R2, show run section router BGP. So I only have BGP with the customer R9. Now I'll run VP and V4 between 5 and 2. So router BGP 100, no BGP default IPv4 unicast, because I don't want IPv4 neighborship. I don't need IPv4 neighborship between 2 and 5 because there's no global routing table exchange. So I can just say neighbor 5555 remote AS 100. Update source loopback 0, address family VPN v4 unicast, neighbor 5555, activate. That's my BGP configuration on R2. Same thing I would do on R5. So step number 4, establish VPN v4 with the true PE of my ISP, which is the core ISP. So no BGP default IPv4 unicast. So you don't really have to give this command. Because if you don't give this command, he would by default activate address family IPv4 also. It's not, there's no any harm in that. There's not a problem in that. I like doing this because, I mean, it's just a habit for me to not activate something that I don't need. So let's do a neighbor 2.2.2.2 remote AS 100. Update source loopback 0. And address family VPN v4 unicast, neighbor 2222, activate. So now 2 and 5 should establish a VPN v4 neighborship, and they should exchange their customers' route, which means 11 and 34 gets exchanged between them. So if I look at now R5, show BGP VPN v4 unicast, all, I should have both the route. I should have 11 and I should have 34. Let's wait to see if I'm learning the routes. I would not learn at this point of time. Why is that? I haven't done step 5 and 6. Over step 5, redistribution. Do I need redistribution? No. Why? Because PECE is BGP. PECE here is BGP. So between 2 and 9, it's BGP. 5 and XR1 is BGP. So there's no redistribution required. I just need to configure step 6, which is import export. So let's do that. So VRF definition ISP2, address family IPv4 unicast, and say route target both. Let's keep this completely different. So let's keep this as 11:34. Okay. And let's do the same thing on the other side. On R2 as well. So now if I check my BGP route, show BGP VPN v4 unicast all, I should see both the routes. So I have 11 and 34 in the routing table or in the VPN v4 learned route. I have a route, and this route is going to be sent to R9 because R9 is the neighbor, right? So because I have the import command, R2 learns from R5, he imports the route in the routing table of ISP2 and sends the route to R9. So R9 should get the route. Let's go to R9 now and check show IP route BGP. I don't see it. Let's do a show BGP. I don't see it. I don't see 34. Let's check XR4. He should be receiving 11. Show BGP. I don't see it. Show BGP. In fact, it's XR1. Show BGP. I don't see it. So they're not getting the routes for some reason. So we have to troubleshoot this. Let's see what the problem is. I don't really know what the problem is. Let's go and troubleshoot this. Let's first go to R2 and see. So I know R2 is getting the route, and I know R5 is getting the route. So show BGP, VPN, V4, unicast all. So I know R5 is also getting the route, which means the core ISP has the routes between 2 and 5. Are they sending the route to the customer, which is the core carrier? Are they sending the routes? Let's check that. Show BGP, VPN, V4, unicast. I believe the command is all. There should be a neighbors. 100.5.31.31 advertise routes. Am I sending? I am sending 11. So I know R5, the core carrier, is sending the route to customer, which is the customer carrier, XR1. Is R2 sending to his customer carrier? Show BGP, VPN, V4, unicast all, neighbors, 100.2.9.9, advertised routes. So R2 is also advertising 34, which means 9 and XR1 should receive the route, which means the problem is not on the core carrier. It should be on R9. Let's do a debug and check why they don't have the routes. Let me first recheck. Yeah, they still don't have the route. Let's do a debug. Debug BGP IPv4 unicast updates. Let's do a clear IP BGP star soft. What do we see? Okay, so I did receive the update of 34. It was denied due to AS path contains own AS. That makes sense. So if I look at the diagram, what is R9's BGP AS number? 1, 2, 3, 4, 5. What is XR1's BGP AS number? 1, 2, 3, 4, 5. You remember the BGP concept. AS path is always prepended. So when XR1 advertises eBGP route to R5, he prepends AS 1, 2, 3, 4, 5. When 5 gives it to 2, there's no prepend happening because that's an iBGP neighborship. When 2 gives it to 9, it's an eBGP neighborship, so he has to prepend the AS. So he prepends AS 100, which means the AS path looks like 100 space 1, 2, 3, 4, 5. Will R9 accept that route? No, because his own AS is there in the AS path. Discard the route, which is a loop prevention mechanism in BGP. So 2 ways to fix this. Either the customer carrier R9 and XR1 can fix that by saying allow AS in, which is kind of a dangerous command. I would not do that. That allow your own AS to come in because that really can cause problems. Instead, I would request the core carrier that, hey, can you override my AS number? So basically the core ISP is going to replace the AS number of the customer carrier with his own AS. So for that, I got to go back to R2, go under my BGP, which is here, router BGP 100. And give the command AS override. Same thing I would do on R5. AS override. Now if I look at R9, on all, show IP BGP, look at the route. He has received the route 34. And look at the AS path, 100 space 100. So this is the one which was replaced. Earlier, it was 100 space 1, 2, 3, 4, 5. That's why R9 was discarding the route. Now the core ISP has replaced the customer carrier's AS number with his own AS number, which is 100 space 100. So now R9 and XR1 should have the route. Show route BGP or show BGP. He has 11. And look at the AS number. Now, all I need to do is somehow tell R11 to get the route. I need R11 to get that route. There's no BGP between 11 and 9. So R9 would redistribute that in IGP. So basically an LDP label gets generated for that IGP route. So there are two ways to do this now. Let's say if there was a BGP between 11 and 9, I could just do a send label between 11 and 9. I could use BGP to send the label. But since there's no BGP between 11 and 9, I could just redistribute the route in IGP, that one specific route, which I'm learning through BGP, redistribute that in IGP, and then IGP takes care of that. LDP will generate a label for that IGP route. So let's go to 9. Under my global OSPF process and say redistribute BGP 1, 2, 3, 4, 5 subnets. So now if I look at 11, show IP route OSPF, in my IGP, I should see 34 as an external route, which means if I do a show MPLS forwarding, I have a label for that, LDP label, 10,002, which is coming from my LDP neighbor R10 in the middle. Same thing I would do on XR1. I believe it is router OSPF1. Yep. So router OSPF1. Redistribute BGP 1, 2, 3, 4, 5. Commit. So if I look at XR4 now, show route OSPF, I should see the route in my routing table 11, 11, 11, 11, which I do, and show MPLS forwarding, I should see a label for 11, which I see from my local LDP neighbor 33, which is XR3. So I believe now customer to customer ping should work. Let's check the customer first. First of all, my VPN v4 neighborship must have come up with XR4. Let's check that. Show BGP VPN v4 unicast all summary. It's still active. It hasn't come up yet. Let's wait. I believe we gave everything. Under VPN v4, we have activate. So looks okay. Let's look at XR4. I have VPN v4 here. I have VPN v4 globally activated and update source. So yeah, my neighborship should come up. So I have the labels in my label stack, but I see the labels, but my VPN v4 neighborship is not coming up. I think it's to do with my transport label broken. Let me in fact go to R11 and do one command just to see. Let's do a ping MPLS IPv4 34 34 34 34 255 255 255 255 source loopback 0 verbose. Just to see if it's broken or not. It is broken somewhere, because I should not see a dot. Let's do a trace route to 34 34 34 34 source loopback 0. Yeah, it is broken. We'll have to see one by one now. So show MPLS forwarding. I have a label 10,002, which is advertised by my LDP neighbor R10. So that's correct. And let's go to R10. He should not see an implicit null, like a pop label. He should see a label advertised by R9, because I have a transport label of BGP between 9 and 2. So show MPLS forwarding. He sees 9004. Now, normally, if there was no BGP between 9 and 2, which is the customer carrier and the core ISP, I would see pop label here. But because R9 is not sending implicit null, he's receiving a label from R2 for the route 34. So he's sending the label via redistribution via LDP to R10. So he's not sending implicit null. So this is correct. So there's no label broken. My transport label is not broken up till R9. Let's go to R9. So in my MPLS forwarding, I won't see anything because the label is not coming through MPLS, through LDP, it's coming through BGP. So for 34, I see 2008, which is actually advertised through BGP. So if I do a show BGP IPv4 unicast all unicast labels, I see 2008, which is advertised by BGP from R2. So till R2, there's no problem. Let's look at R2. Show MPLS forwarding. 34 from R5. This is a VPN label, which you can see here. This is a VPN label packet. So till R5, VPN label is fine. And there would be a transport label to reach R5, which is 5555 going to R3. So till R5, no problem. Let's check R5. Show MPLS forwarding. So for 34, I see a BGP 31005, which is a VPN labeled packet, which is correct. That looks okay. Let's look at XR1. Show MPLS forwarding. I think, you know what? I think I know what the problem is. Show run router static. Yeah. So XR routers, they kind of have a thing that they can only label switch /32 routes. So if I look at my routing table, show route, my global table, what's my next hop to reach 11.11.11.11 for the reverse traffic? For 11.11, my next hop is 100.5.31.5. And if I look at my routing table, I have 100.5.31.0 / 24. Since my next hop in the routing table is not a /32, it cannot label switch. So this is only on XR routers. So for you to label switch, you need the route to be a /32. The next hop needs to be a /32. So I'm just going to create a static route for that next hop. Router static, address family IPv4, unicast, and say 100.5.31.5, which is my next hop, R5, the core ISP, /32. Interface would be gig 0000.531. Let's do a commit. So show run router static. The reason I gave that is because now if I look at my routing table, I have a static route entry for the next hop, which is a /32, which means if I look at my MPLS forwarding table, since my 11.11.11.11 is a /32 here, next hop is a /32, it should be able to label switch now. If I go back to our 11, my BGP VPN v4 neighborship came up. So that was basically the issue. It's kind of like a thing with XR routers. XZs don't do that, but XR routers do that. So they really cannot label switch if the next hop is not a /32. So now I have my BGP neighborship. Let's do a show BGP VPN v4 unicast all. I have the customer route 17 and 18, which means my customers are 12, which is green OSPF. If I do a show IP route OSPF, he has 17, 17, 17, 17. Can I ping 17, 17, 17, 17, source loopback 0? End-to-end ping, customer to customer ping is working. Let's check R13 also, which is BGP. Show IP route BGP. He has 1818 learned through BGP. If I do a ping to 1818, source loopback 0, my ping works customer to customer. Let's look at the trace route and look at the label stacks. How many label stacks should be there? Let's write it down. Where is it? I need to connect. Okay. Okay. So okay. So this is, let's say if I'm doing a ping from R12 to R17, this would be an IP packet coming here. IPv4, because there's no MPLS between customer and PE. R11 would encapsulate the packet with a VPN label which XR4 has given him. Okay, because XR4 and R11 are VPN v4 neighbors. So XR4 tells R11 that if you want to go to my customer R17, you need to encapsulate with a VPN label that I'm giving you. So R11 will encapsulate with a VPN label. And on top of that, he would encapsulate with a transport label, which R10 through IGP, through redistribution, which R9 had done, he would put a transport label. So when he sends it here, you would see something like this. You have your IP, you have your VPN label of XR4, 34, something 34, and then a transport label from R10. R10, when he sends it here, he would swap the transport label. The VPN label remains unchanged. He would swap the topmost layer, which is the transport label, through LDP again, and he would put the label which R9 has given him, which means going here, you would see IP, you would see 34, and you would see R9, R9's label. R9, when he sends it down, he is going to swap the transport label again with not the label learned from LDP, but the label learned from BGP. So again, you would see IP, you would see your VPN label 34. This is your VPN label. And then the transport label learned through BGP, which would be R2's label. When R2 gets it, because this interface is in the VRF, R2 would obviously, when he gets 2002, he is going to swap the transport label with a transport label which LDP has given him through R3. But before that, he would put the VPN label which R5 has given, because there's a VPN v4 neighborship between 2 and 5. So when R2 sends it down here, you would see something like IP. This would still be 34, the VPN label from XR4, unchanged. There would be another VPN label, which R5 has given. And on top of that would be the transport label, which R3 has given through LDP. So this would be R3. Packet comes to R3. R3 swaps. This part remains the same. So this part is the same. So I have IP 34, I have 5, and this would transport label would change to R6's label, which R6 must have advertised to R3. Then going here, same thing. This part remains the same. This would change to R4's transport label. When R4 gives it to 5, he would do a penultimate hopping, which means my transport label gets removed now. So what goes here is a VPN labeled packet. So you would see IP, you would see VPN label 34, and you would see another VPN label 5. There's no transport label there. When R5 gets a VPN labeled packet, what does he do? He does no label, which means remove that topmost layer. So he is going to remove this VPN label and put a transport label, which XR1 must have advertised through BGP, which means going here, you would see IP. This would still be 34 VPN label, and this would be a transport label which XR1 31 has advertised. This is through BGP. XR1 sending it down is going to swap the transport. This part remains the same now. So this will still be IP 34, and transport label would be of XR2, which is 32 through LTP. This would change to, this part remains the same. This would change to 33. Transport label changes to, in fact, this is 35. This would change to 33. When XR3 gets it, he does a penultimate hopping and removes the topmost layer, sends a VPN labeled packet to XR4, which means XR4 gets IP and a VPN labeled 34. When XR4 gets it, he removes the VPN label, looks at that which customer it belongs to, that label, and forwards it to green, which means it's an IPv4 packet going to customer. This is what you should see. So 2 label stacks here, 2 label stacks here, 2 label stacks here. From R2 onwards till R4, you would see 3 label stacks, 2 VPN labels, 1 transport label. On R5, R4 would send he would remove the transport label, send a VPN label packet to R5. Then again, 2 label stacks, 2 label stacks, 2 label stacks, 1 label stack, and then IPv4. This is what you should see. Let's do a trace route and verify that. Okay, let's go back and do a trace route from customer R12, trace route to 17, 17, 17, 17, source loopback 0. We should see an IP packet first going to the true ISP R11. That's an IP packet going to R11. R11 should encapsulate with a VPN label of 34, and on top of that, an LDP label of R10. So 34 is VPN label coming directly from XR4, and transport label coming from R10. R10 swaps the transport label with R9's label and forwards to R9. VPN label remains the same. R9 would swap the transport label with the BGP learned label through labeled unicast. VPN label remains the same. Now R2 would now put a VPN label on top of your VPN label. This is your original VPN label. There's a VPN label of R5 and a transport label through LDP of R3. R3 swaps that with R6's transport label through LDP. R6 would swap that with R4's LDP label. Again, that's a transport. R4 will do a penultimate hop popping, remove the transport label, send a VPN labeled packet to R5. R5 now removes the VPN label and now adds a transport label learned through BGP labeled unicast of XR1, which you can see here, 31,000. That's your BGP transport label. XR1 swaps the transport label with an LDP label learned from XR2, which is this one. VPN label remains the same. XR2 would swap the transport label with learned from XR5. XR5 would swap the transport label learned from XR3. XR3 does a penultimate hop popping and removes the transport label, sends a VPN label packet to the true PE XR4. XR4 receives just a VPN labeled packet. There's no transport label. XR4 does a routing lookup. He sees this belongs to customer green and forwards IP packet to customer, which you can see here. That's your carrier supporting carrier. So in short, if you look at the list of things that we did for a quick recap, R11 and XR4 would form a VPN v4 neighborship with each other. And R9 and R2 would form a labeled unicast BGP neighborship. R5 and XR1 would form a labeled unicast BGP neighborship. R9 and XR1 would do a redistribution in BGP when they learn the route. And besides that, all the true PEs, R11, XR4, R2, and R5 would treat their customers as customers. That's all 6 steps basically. That's all we did on all these routers. And one more thing, XR1 needs to have a static route for the next hop to R5. Otherwise, he would not label switch. That's all we needed for carrier supporting carrier. Now, this design it's really scalable because think from a core ISP perspective, he can have thousands and thousands of smaller ISPs connected to him. So basically, small customer carriers, they don't really need to maintain their own MPLS end to end. They can just connect to a core ISP and get connectivity for their customers. So they don't really need to invest in infrastructure end to end and run MPLS or run segment routing and maintain all of that. They can just connect to a core ISP, and core ISP can give you connectivity by still segregating the customer route. So core ISP has no knowledge of which customers, what routes are coming in. For him, the customer is R9 and XR1, which is the customer carrier. He has no view of the actual customer. And the best part about this is that if you look at the VPN label, it's end-to-end same. So whatever our XR4 had advertised to R11, it was end-to-end same. Look at this, 34010. That remains the same end-to-end, which means that QoS and everything can be retained and can be maintained, whatever you're doing from the customer carrier's perspective or even the customer side. So a lot of advantages of doing this. It's highly scalable and something that you would always see as an implementation when you have customer carriers and core ISPs. Okay, so I hope you guys enjoyed this webinar. I will now answer some questions. Let me check what questions we have. So I see a question that is the concept of carrier supporting carrier similar to seamless MPLS, since in both cases, LDP or segment routing transport LSPs is broken. It's pretty much similar. So in both the cases, yes, the transport label is going to be broken, but you need to fix that. Obviously, the ways would be different, but the concept is pretty much the same. I see another question. Could you use VRF aware LDP instead of BGP labeled unicast? You could use VRF aware LDP, but I doubt that ISP would probably want to run that. I mean, if it's a lab environment, yeah, but production wise, I don't see any ISP agreeing to do that. I mean, I've worked with a lot of ISPs. Trust me, sometimes they're a pain in the ass. I shouldn't be saying that actually. Then I have a next question. Is that sub interface for VRF? I don't know what that means. I have sub interfaces on all the routers. It doesn't really matter whether it's a sub interface or a physical interface. Can you show us the final config for each device or make it available for download? Yes, I can. What I can do is I can download this config and maybe give it to the production team, and they would probably figure out a way to give it to you guys. I see another question. Is there a way to disable behavior shown where iOS XR won't label switch traffic over routes that are non/32? I don't really think that there is a way to disable that. That's how it's always been. I mean, I've worked on different versions of platform for the XR, right from 4 to 5 to 6 to 7. It's kind of always been that way. So yeah, I don't think you can do that. At least I don't know if there's a way to do that. But if you know about that, let me know. But I don't think there's a way to do that. It's always been that way. Then, so I see another question. I'm not sure, but I think we do configure IPv4 unicast on XR4 and not VPN v4. If that's true, why? We didn't configure IPv4 on XR4. We configured VPN v4 on XR4 with R11. And there was IPv4 with the customer under the VRF. You can do IPv4 also with R11. That's in case, like I said, if you have some global routing table routes that you need to exchange. Let's say maybe the core ISP is giving internet access to the customer carrier, then probably you may have global routes also. So in that case, you may want to exchange even IPv4 address family. In our case, we didn't have really internet access, so it was just customer to customer. So we just required VPN v4. Then I see another question. Does sites of ISP2 must share the same AS number? They don't need to have the same AS number. Usually it would be the same, but it doesn't need to be the same. Then I see one last question. Sorry, I mean XR1. I don't know what that question is. Or maybe it's from the previous question. Yes, so I see a question, which I think he's corrected his question, that do we need to configure only IPv4 unicast on XR1 and not VPN v4? Yes, only IPv4 on XR1 towards the core carrier, but that's not a normal IPv4 BGP. It has to be a labeled IPv4 unicast because your transport is broken. So it needs to be a label. You don't need VPN v4 because XR1 is a customer. He's not he's not connecting to any customer himself. XR1 is a customer for R5, for core carrier. He himself is not connecting to any customer. If you look at the diagram, XR1 is here. He's a pure customer for R5. But XR4 is is a customer for R17 and 18. So XR4 would be a true PE, and XR1 is not a true PE. He doesn't connect to any customer. He's just a normal customer, like a normal customer edge router. But the only difference is that he's doing a labeled unicast BGP. I hope that makes sense. And yes, I will download these configs and the diagram. So if you want to try it out on maybe any virtualization softwares, you can probably try that out. I hope you guys enjoyed this webinar, and I will see you in my next one.